all these ideas of molar mass, percent composition, we want to put it all together in what's called elemental analysis. So elemental analysis is the process of determining molecular formula for an unknown compound. So for example, you find white powder and you want to know what it is, right? You have no idea, you can't, molecules or compounds don't come with signs saying this is my molecular formula, right? You need to know what it is. How can we do an experiment to determine this, what it is, what elements are in there and how many of those elements to determine the formula and therefore all the properties, its name, all that good stuff. So if you're gonna do it, step one is you burn it. When you burn substances like this, you can actually get percent composition. So that's actually why percent composition is useful, because it's relatively straightforward to obtain from experiment. You can just burn the compound. What ends up happening, we'll talk more about this in chapter 4, but when you burn compounds, you react them with oxygen and basically you break all of the atoms apart that are in the compound. Say this sample that is right here, all of the atoms in there get broken up into compounds of those atoms with oxygen. And so basically if there was hydrogen in here, it would become water. If there's carbon in the sample, it becomes carbon dioxide. So you do this, what's called combustion analysis, where you burn it in oxygen and then you analyze, you look for the different possible products. So how much hydrogen was in there, how much carbon was in the original compound, those sorts of things. And so what that gives you is percent composition, right? Because you measure a mass of water, that gets you a mass of hydrogen, that tells you the mass of hydrogen that was in this original sample. You can get the mass of carbon, get all those things, and you can determine percent composition. So percent composition is kind of a pain to calculate from a formula, but you can't get a formula directly from an experiment. You can get percent composition. The percent composition you get from those experiments allows you to determine the empirical formula of the compound you're analyzing. Empirical formula is not a molecular formula. It's a little bit less useful, but that word empirical implies that it comes from an experiment. You can't just perform a single experiment and determine a molecular formula. Instead, you have to get this empirical formula, which comes directly from the percent composition. You analyze the percent composition that came from that burning experiment that we just talked about. And so what an empirical formula is it's a simplified ratio of the atoms in a compound. It's not the absolute number. So empirical formulas, it's a process we've seen before with ionic compounds. So for example, N2O4, both of those numbers are divisible by 2. But since it's a covalent compound, we don't simplify it. That molecule is 2 nitrogens and 4 oxygens. The empirical formula, we would simplify to 1 and 2. It's important to note, this does not reflect the total number of atoms of each type of element in the molecule. It instead reflects the ratio, 1 nitrogen for 2 oxygens. In the case of, say, something like water, the empirical formula just is the molecular formula, right? They're the same thing because it's already simplified. The reason why empirical formulas are less useful is that multiple compounds can have the same empirical formula. C2H4 goes to CH2. C6H12 goes to CH2. So those are the same level, the same empirical formula, because those compounds have 1 carbon for every 2 hydrogens. So that sort of empirical formula, it can't, if you determine the empirical formula of a compound, you can figure out things that it isn't, right? You have restricted it to certain, say, family or a subset of compounds, but you can't be pure, 100% certain. If you find that the compound has an empirical formula of CH2, there's a lot of compounds with the empirical formula CH2. It's not NO2, right? Because there's no nitrogen in it. It's not water, but you don't know which one of the compounds with the empirical formula CH2 it is. All right, so here's the process for how you do elemental and how you get empirical formula. So we'll walk through this example, but it's basically 3 steps. You find the mass of each element in a 100-gram sample. You convert from grams of each element into moles, and then you identify the mole amount that's the smallest and divide the others by that value. So it's a 3-step process. We'll walk through an example as opposed to kind of walking through this. There's also an example in the slide. There's an additional example in the slides with work shown. So we have our unknown white powder, the one that we burned. So we had our unknown white powder, we burned it, and we got the following percent composition: 49.5% carbon, 5.2% hydrogen, 28.8% nitrogen, 16.5% oxygen. What is the empirical formula? So let's walk through this example, see how it goes when we follow those 3 steps. All right, we have the percent composition. Now I want to know the empirical formula. So we burned our white powder, we got our percent composition. I want to see how that processes into an empirical formula. So we know with percent composition, what we said we can do is if we have a mass of compound. So what I'm going to do is I'm just going to suppose that it's 100 grams of this unknown compound. You can choose any number you want because we're just supposing it, right? 100, we're going to see, makes our lives easier. So say I have 100 grams of the compound, I know if I want to figure out the actual mass of carbon, I just multiply it by the 0.495, right? Where this was the percent composition of carbon. And here I'm just using it as a ratio. And I can always just multiply that decimal version by the mass. And I would get that in this compound, it's 49.5 grams of carbon. And so the reason why I choose 100 is because it basically just makes it easier. If you chose a different number, if you chose 3,000 grams or 26.254, you could do that. You just have to actually calculate that out. But otherwise, because we use 100, we just basically can take the value of the percent and change it to grams of that. So similarly, our 100 grams times the 0.052 gives me 5.2 grams of hydrogen. The 0.288 gives me 28.8 grams of nitrogen. And the 0.165 gives me 16.5 grams of oxygen. And so we can see just by choosing the 100, that's just kind of, we just know that the values, those numbers that we had as percentages, just become grams of each particular type, which is great. So what I want to do with these now is, now that I have masses of my different atoms, this is what percent composition gives us. But what we want is an empirical formula. We want those coefficients, the subscripts, sorry. And those subscripts represent counting the number of atoms. So what I'm going to do is I'm going to take this mass representation and turn it into a counting-based representation. Namely, I'm going to convert all of these masses into moles. This empirical formula determination is a big process of calculating molar masses, using molar masses, converting back and forth from grams and moles. That's why we're talking about it now. Get some good practice at converting. So I can look all of these up. 1 mole of carbon is 12.01 grams of carbon. 1 mole of hydrogen is 1.01 grams of hydrogen. 1 mole of nitrogen is 14.01 grams of nitrogen. And finally, 1 mole of oxygen is 16.00 grams of oxygen. And so from that, I can calculate it out, and I have gotten, this is 4.12 moles of carbon. This is 5.1 moles of hydrogen. And this is 2.06 moles of nitrogen. And this is 1.03 moles of oxygen. So what I've done is I've said, suppose I have 100 grams of this compound. I can use the percent yields that I got from another experiment. I can say, well, what's the mass of each compound, of each element in this sample compound? And then I can turn those into moles. So now I have a counting unit representation of the different atom types in my compound. What I want to do is find the one that is the lowest of these numbers. So 4.12, 5.1, 2.06, 1.03 is the smallest value. because that's what that smallest value, what I want to do is divide the other values by that to determine the ratio. Okay, so what I'm going to do, let's scoot this up. We're going to do 4.12 moles of carbon per 1.03 mole oxygen, and that gives me 4. I'm just using the numbers, 4.2 moles divided by that 1.03. I have the 5.1 mole of hydrogen divided by the 1.03 mole of oxygen. When I divide that, I get 4.95. I have the 2.06 moles of nitrogen divided by 1.03 moles of oxygen, gives me a nice 2. And then 1.03 mole of oxygen is as expected, divided by 1.03 mole of oxygen as expected, 1. And so what these numbers tell you is that for every 1 mole of oxygen, there is 2 moles of nitrogen, 4 moles of carbon, and this isn't quite there, but we're going to round that to approximately 5. So these numbers that we've calculated end up being the subscripts. So C4, H5, N2, and then O. So that ends up being my empirical formula. We saw when we were comparing moles, wanted to know how many moles of carbon were in, say, a mole of this compound, we'd say 4, right? 4 to 1. For every 1 mole of oxygen, there are 2 moles of nitrogen, 5 moles of hydrogen, and 4 moles of carbon. That's the idea of doing this division here. You're figuring out those ratios, which equal the subscripts. And so we can see how those all go together. When you do these divisions, sometimes you'll get things, this is, like 2.000, there's all that stuff on sig figs. But oftentimes you'll get values that are kind of close, not quite to 5. But these subscripts down here always need to be whole numbers. There should not be decimals down here. So when they're close like this, 4.95, that's where you can round. If it's not, if you get like a 4.7, you can't round that. You need to adjust with that. We'll talk about that here in a little bit. But generally, they're going to be really close to whole numbers. Or fractions, and so you can deal with that. But you want to round it to that nearest whole number, because this should not be 4.9. There's not 4.9 atoms in a molecule. It needs to be a whole number. 1, 2, 3, 4, 5. Those are counted exact numbers. When you're working with empirical molecular formulas, the subscripts that you're writing are representing the number of atoms in a molecule, or in the ratio, but they should always be whole numbers, never decimals. Those are counting values, those are exact. But when you do this analysis, when you do that division by the smallest number of moles, you don't always end up with perfectly integer numbers. In fact, they generally are close, but not quite. And so what we want to do is round those decimal values to the closest whole numbers. But we only want to do that when they're really close. So for example, 1.97, that should become 2. 4.03, that becomes 4. When you're doing that rounding, it should be a very, very small amount of rounding. If you instead got a molecular or an empirical formula like 1.05 and 1, we should instead be multiplying those ratios out into whole numbers. So basically this ratio is 1.5 to 1. That's the same as 3 to 2. So you multiply both of those coefficients by subscripts, by 2. And you do that anytime you see like a 0.5 back here. That is, you would not want to round that to 2. In order to round to 2, it needs to be very close to 2, like 1.95 or higher. If you have, say, a 0.33 or a 0.66, all of those subscripts need to be multiplied by 3. If you have a 0.25 or a 0.75, all of those subscripts need to be multiplied by 4. You won't get anything too much more extreme by that, but you're looking at basically it's representing a fraction, and you want to get that all into whole numbers. But again, never want decimals in your subscripts. We've gotten the empirical formula, which is great, but we want more. We want that molecular formula. We want to definitely know what the compound is. So in order to get that, you have to do a second experiment. You have to do another experiment where you obtain molar mass. So we're used to getting molar mass from the molecular formula, reading it off the periodic table, but you can't do that if you don't know what it is. So there are experiments you can do in order to figure out what molar mass is. So what you're going to do is divide the molar mass by the mass of the empirical formula to figure out what the molecular formula is. So let's take a look at what I mean by that. So you figure out the molar mass of the compound. That comes from an experiment. You have the actual formula of the empirical formula, you know, the elements and their subscripts. So you compute this molar mass of the empirical formula. Well, what ends up happening is you're basically dividing out what is the mass per empirical formula out of the entire mass of the compound. And it gives you this whole number. The reason why you expect it to be a whole number is because when you simplified the molecular formula into the empirical formula, you divided a whole number out from all of the subscripts. You're trying to get that whole number back. That whole number can then multiply by all the subscripts in the empirical formula to get you back your molecular formula. So let's see this in action. Let's take a look at an example. We're going to keep on analyzing our same white powder that we've looked at previously. We did some experiments on it and we found the molar mass was 194.19 grams per mole. From that, I want to know what is the molecular formula of this unknown compound. Okay, analysis of the unknown powder gives us a molar mass. We want to know molecular formula. So when you're given the molar mass, this is our same unknown powder. So we want to start with the empirical formula that we had from before that we just calculated, and I just lost it. What is it? C4H5N2O. So what I want to do is I want to compute the mass of this. And I get that. It's going to come from the 4 times the carbon plus 5 times the hydrogen plus 2 times nitrogen, 1 times oxygen. 1 grams per mole, 5 times 1.01 grams per mole, 2 times 14.01 grams per mole, plus 16.00 grams per mole for my oxygen. So again, I'm just using, this is how we've previously learned. You just use the formula, get the subscripts out, that's your number of each atom, look up the masses on the periodic table. We get the mass of that is 97.11 grams per mole, which is great. So what I'm going to do then is I'm going to take the overall molar mass, 194.19. That's the mass of the whole compound. I'm going to divide it by the mass of the empirical formula, and I get 1.9997, which is 2. When we're doing this process, dividing the mass of the entire molar mass, the entire compound, by the empirical formula, we generally are expecting to get a whole number, something close to a whole number that should be rounded to 2. What we're literally doing here is saying this is all of the mass. What is the mass of the simplified empirical formula as a ratio of that? And the ratio is 2 to 1. So what that tells me is that my molecular formula is going to be equal to 2 times the empirical formula. So 2 times C4H5N2O is equal to C8H10N4O2. Where I take that 2, and we can see this is just doing the opposite process of the empirical formula, right? Getting the empirical formula was simplifying those values. Saying if we look here at the molecular formula, 8, 10, 4, and 2, all of those are even. They're all divisible by 2, so we can divide out by 2 to simplify it. And so we can get overall C8H10N4O2. That is caffeine. So the powder in the picture is actually caffeine. So it looks like, and this is the process we go through. So if you burned the unknown powder,
You do another experiment to determine the molar mass. You can figure out, just being given a chemical, this is a sample of matter, what is it? You can determine the molecular formula using analysis based around kind of the mass representation and the mole representation, and working to determine information about an unknown compound.
All right, another video down. No questions for participation 6-9 yet, but plenty more videos to go. See you in the next one.